Good morning, everyone. Thank you for being here today. My name is José and I'm a postdoctoral researcher with the NOS project and an initiative launched CiTIUS to develop resources, models, applications that support the Galician language. It's my pleasure to introduce our guest, José Moares Guedes, for today's doctoral meeting. I sincerely thank him for joining us and for sharing his research. A few years ago, I had a conversation with Manuel Casalodeiro. Do you know it?
No.
Okay. An independent researcher and former computer engineer who shifted his career focused to climate change and sustainability. He shared two radical ideas with me, the best sense of word. They stem from the root of the issue. First, that we shouldn't call it climate change, but rather climate chaos. And second, that our world is overwhelmingly dependent on fossil fuels, which are far from sustainable. He also highly recommend a book to me, Petrocalypsis, by Antonio Turiel, as a physics researcher. A work that deepened my concerns about our current energy system. Reflecting on these ideas has made me appreciate the importance of finding real solutions. That's why it's a true privilege to welcome someone who not only researches, but also actively works on practical ways to address climate chaos and reduce our dependence on fossil fuels. Today, José Moares Guedes will present his thesis on organic solar cells, an innovative and promising field in the search for sustainable energy alternatives, supervised by his director, Antonio García and co-director Natalia Serrano. José is a physicist with a master's in renewable energies, climate change, and sustainable development from the University of Santiago de Compostela. But what I find particularly relevant is his commitment to collective action. He served as a student delegate during his master's and was also a member of his high school council, demonstrating his belief that tackling these challenges is not just about research, but also about social implementation. So we'll have 20 minutes to present his work, after which I will open the floor to your questions. Please join me in giving him a warm welcome. Thank you very much.
Thank you. Okay, shall I start? Okay. Hello, my name is José, and I'm going to present my work here titled Modeling and Optimization of Organic Solar Cells. In this doctoral meeting, we are going to discuss the following contents. Firstly, we will give some introduction and explain the objectives of my work. Then we will see some fundamentals of the solar cells, such as the solar spectrum and the energy band gap. Then the generation and the recombination processes, and the figures of merit used. After that, I'm going to talk about the modeling of experimental organic solar cells. And then I'm going to show you the results obtained from the model solar cells and the optimized solar cells. And finally, I'm going to explain you some conclusions. Let's start with the introduction and the objectives. First of all, we live in a context of global warming. So, under current policies, global temperatures could rise 2.4 degrees at the end of this century, exceeding the critical limit of 1.5 degrees established in the Paris Agreement. So, to mitigate this, the concept of net zero appears, which involves balancing greenhouse gas emissions with their elimination, restoring balance to the carbon cycle. To avoid catastrophic impacts, emissions must be reduced by more than 45% by 2030. And according to the International Energy Agency, triple renewable energy capacity is essential to reduce emissions before 2030. As I previously mentioned, in this context of climate change, the rate of renewable energy needs to be increased. In this figure, I present the number of gigawatts of renewable energy capacity per year. Showing here, this light blue is according to the solar photovoltaics, the dark blue to the wind energy, the light green according to the hydropower energy, and dark green to the bioenergy. And we have yellow, other renewables, which is insignificant in for these years. To achieve the net zero scenario in 2030, we need to increase so much the capacity of renewable energy. As you can see here, we need to increase from more like 5,000 gigawatts to more than 11,000 gigawatts. And here I present two cases for 2028. Under current policies, if we follow this trend, we only achieve this main case, which is not enough for achieve all the goals established in the Paris Agreement. But in an accelerated case, which is an optimistic case, we need to increase to around more than 8,000 gigawatts if we want to achieve this scenario. Finally, if you can see here, the solar energy is the most abundant. And why? Because it's clean and a safe source of energy. In this table, I present the solar cell types with their efficiencies, market share, and some advantages and disadvantages. First of all, the monocrystalline silicon cells has the biggest market share, around 30 to 40%, with an efficiency of 27%, because are durable and, well, they have a disadvantages, which is the cost, they are expensive. Then the polycrystalline silicon, with a market share of 30 to 35% approximately, with efficiencies around 22%, they have lower cost than the monocrystalline and lower efficiency. Then those made of amorphous silicon are much cheaper and flexible, but have lower efficiencies, around 10 to 12%, which a market cap around only 5 to 10%. Also, they present as a disadvantages, which is the short lifetime. There are also other types of technologies, like the thin film cells and the perovskites. The thin film has a market share of around 10 to 15%, with efficiencies good, around 15 to 20%, but their lifetime is very short, and they are flexible and has a low cost. In the case of the perovskites, they have good efficiencies, around 20 to 25%, but they are unstable and are in development. However, in this work, we focus on the organic solar cells, which have efficiencies around 15%, are very low they have very low cost, and they are flexible. But why organic cells instead of the other types of cells? When we compare the organic solar cells with silicon cells, these are presented as a cheap option. They are light and flexible. They are easy to manufacture. There are abundant raw materials, and they are environmentally friendly. In fact, the organic solar cells are the lowest carbon footprint among all. Also, their efficiency is increasing from values below 3% in the 1990s to over 15% in recent years, and rapid improvements suggest that the efficiency is going to be more and more increased. Well, when we compare, the manufacture of highly efficient organic solar cells is a complex process. So device modeling will allow us to optimize their performance before production, saving significant cost, saving time, and saving effort, which is so important for the industry. Therefore, in this work, we focus on understand how an organic and polymeric solar cell works, model and characterize two experimental organic solar cells, and then optimize the organic solar cell performance to maximize the electrical energy generation. Let's start with the solar cell fundamentals. First of all, for a solar cell to work, we need light. So the AM1.G spectrum shown here is the standard for measuring cell efficiency. Also, another fundamental concept is the energy band gap, which is the minimum energy to overcome to create the charge carriers. With this relationship with the wavelength. For example, if we have a material with energy band gap of this value, 1.37 electron volts, it thus means that with wavelengths shorter than around 900 nanometers, we can absorb all these photons and create carriers. In this slide, we can see the main processes that occur in an organic solar cell. First, all the photons procedent from the sunlight are absorbed in the active layer, creating excitons. These excitons must diffuse to the acceptor-donor interface, and here the electrons and hole separated, and after that this electron and this electron must travel, the electron must travel to one contact and the hole to the another contact. So the number of carriers created due to the absorption of photons is called the generation rate, and the opposite processes is their combination, giving up energy. Here I present the figures, the main figures of merit that we use to characterize the solar cells. Here you can see the current versus voltage curve, called the IV curve in red. From this curve, we can extract the short circuit current, which is the current at 0 voltage, and from here you can see the open circuit voltage, which is the voltage at 0 current. Also, from the power voltage curve, called PV curve, here in blue, we can extract the maximum power, and with this point we can extract the voltage and current at this point. With these variables, we can calculate FF, which means fill factor, here represented. The fill factor graphically is a measure of the squareness of the solar cell. The more square, the better is the cell. And with all of this data, knowing this and knowing the input power, we can calculate the efficiency of the solar cell. Let's move on to the modeling of the experimental organic solar cells. Among all the types of the organic solar cells, we will highlight the bulk heterojunction ones, which is represented here as an example. These cells are formed by a mixture of two semiconductor polymers. Here you can see the main structure, which is first one transparent electrode made generally from ITO. Then we have the hole transport layer and the electron transport layer, which act to facilitate the transport to the electrons and holes, respectively. Here is the active layer, which is formed by two semiconductor polymers. And finally, the metal contact with a low work function. This figure illustrates the structure of the experimental organic solar cells fabricated by researchers at Rovira y Virgili University in Tarragona. Here, I present the thickness of each layer. Note that all of them are in the nanometric scale. For example, in the silicon ones, the scale of each layer are around microns. The structure follows as you can see here. First, the transparent electrode made by ITO. Then we have the P dot and the PDINO acting as the transport layers of holes and electrons, respectively. Here is the metal contact made by silver, and these are the active layers. the first semiconductor are as a donor and the second one as an acceptor. In this table, I summarize the key experimental parameters for each organic solar cell. The fixed values in this table are directly taken from experimental works, and the parameters expressed as ranges are not explicitly reported and require fine-tuning. Here you can see the active layer thicknesses, the work functions of ITO and silver, and the transport layers, the affinity, the relative permittivity, the band gap energy, the lifetimes of electrons and holes, respectively, and the mobilities of electrons and holes, respectively. Furthermore, to accurately model the real solar cell, we need to take into account the resistive effects. Here you can see an equivalent circuit of a real solar cell. This element indicates the current created by light. This element is a diode which simulates the behavior of a solar cell, and these are the series resistance and shunt resistance. In our case, the series resistance is insignificant, so we are going to ignore that. But the shunt resistance requires modeling. So we model as follows as here. First, we are going to extract the current density of the ideal IV curve. Then we simulate the IV curve of a structure that behaves like a metal, which is the shunt behavior. And with both cases, we can calculate the net output current density using this expression, being alpha a calibration parameter. And this calibration parameter was adjusted to fit the experimental results using these values for each organic solar cell. To evaluate the photovoltaic performance of the devices, the current density curves were simulated at room temperature. We sweep the voltage from -1 to 1 volt. We simulate at dark conditions, which means without illumination, and under the AM 1.5G solar spectrum, with light intensity of 100 milliwatts square centimeter. Now let's see the results. This figure shows a comparison between the experimental and the calibrated curves of the PM6 organic solar cell under both illuminated and dark conditions. Note that the simulated curves perfectly match the experimental ones, validating the accuracy of our modeling. Similarly, in this case, from D18 organic solar cell, we have the same behavior. Both calibrated and experimental curves perfectly match, validating the accuracy of our modeling. Well, one of the main objectives of my work is to optimize the devices. So now that we have calibrated our cells, we can reproduce them even when we change these properties. So we can start to optimize. The optimization of the organic solar cells was performed using a multivariable Bayesian software combined with a local search algorithm. We will improve performance and electrical characteristics, and the optimized parameters are the active layer thickness and the work functions of the anode and the cathode. Here you can see the graphical results. These figures compare the optimized, calibrated, and experimental curves under illumination. This is the figure from the PM6 organic solar cell, and this from the D18 organic solar cell. As you can see, the optimized devices show an improvement in performance compared to the experimental and the calibrated ones, especially from this case, from the PM6 organic solar cell. Here in these tables, I present the numerical results. The first table shows a comparison between the experimental and optimized design parameters for the active layer thickness and the work functions of the anode and the cathode. As you can see, the anode work function was increased to 5.8 electron volts, and the cathode work function was reduced to 3.5 electron volts. This could improve the open circuit voltage and the fill factor, as you can see in the second table, for each organic solar cell. Also, the active layer thickness was modified for each organic solar cell. In the first case, this thickness was increased from 0.1 microns to 0.159 microns. This improved the short circuit current in this organic solar cell. In the second one, the active layer thickness was reduced slightly, and this improves the fill factor. And finally, with all this data, you can see the improvements in the efficiency. For the first organic solar cell, I can improve from 16.5% to 23.7%, which is an increase of 7% efficiency, which is a lot. And for the second one, we increased the efficiency from 14.5 approximately to 15.7. This means that the manufacturers in the Rovira i Virgili University manufacture this cell much better than the first one, because when we optimize these cells, we can achieve a big difference between the calibrated and the optimized, but here not. So this cell is well done fabricated. And finally, some conclusions. The organic solar cells are a sustainable and low-cost alternative to fossil fuels for electricity generation. And device modeling will allow us to optimize the organic solar cell performance before production, saving significant cost, saving time, and saving effort. Also, the simulated curves reproduce very well the experimental ones, validating the accuracy of our modeling. And finally, it was possible to improve the efficiency, increasing by more than 7% for the first organic solar cell and only 1% in the second one. And thanks for your attention. That's all.
Thank you very much, Jose. It's time for questions. So if you got some questions, it's now.
I have several. Thank you for your presentation. It was very nice presented. I actually have a question. You can go back to the slide 21, please.
Here?
Yeah. Now you said that you are considering the shunt resistance in your modeling, but not the series resistance. Typically, the series resistance is the parameter that affects the most in the current technology for all photovoltaics. So I was wondering why is that so? So I know shunt resistance can be very important, but why not considering series resistance in this case?
In our case, our collaborators in the Rovira i Virgili University provide us that information. So the zero resistance was around 0.9 ohms. So it's so low, as a value so low, and the shunt resistance was not.
All right. So because how is the size, the actual size of these?
Of these cells?
Yeah, not the active layer, the illumination area.
The illumination area. Our collaborators made cells around only 1 square centimeter, approximately. I don't know about the fingers.
Yeah, so the cell is very small, so
yes.
Yeah, so not considering at this stage. But if this technology is made for printing big layers of organic, if I'm correct.
Mm-hmm.
So in that case, will be an issue, the series resistance in more bigger cells.
It could be. Here, for example,
what's your take on this?
In this photo here, you can see an example of the organic solar cells integrated in a wind farm. And here, I think that the contacts are, well, the rate in silicon, I think, is around 3%, if I am not mistaken. But
Of shadowing, you
yes,
use,
yes. In these cases, where all types of organic solar cells are still in development, they are not explicitly value like magic value to optimize the performance, introducing fingers or introducing the contacts. So, well, it's a field that we can research.
Yeah, because the contact is an ITO.
Yes.
So it's full covered on the ITO.
Mhm.
So you probably you don't have problems on series resistance because of that. It's transparent. Yeah, it's transparent.
It's transparent.
So maybe you don't have problems with series resistance because of that. Yeah. Yeah. Okay. Thank you.
Is there any other question?
In other countries, thank you very much for your nice presentation. In other countries, you don't ask means that you are sleeping during your presentation. They prefer to ask. Or you are doing other things. Okay. Regarding the table, can you go to the, thank you for your nice presentation, Hito again. The first table.
Here,
No, in the second or third slide, I don't remember.
do you remember the slide?
The slide with the 9 or
Nine.
something like that, or 8.
Okay.
This.
Yes.
I have a curiosity. How much is a higher cost or a low cost?
Yeah.
Because
Okay. Well, I searched this kind of information a few days ago, and well, Google said to me that, for example, for monocrystalline silicon cells, it depends on the manufacturer of the processes and the company, but around between 200 and 400 euros per panel. It depends on the technology and the fabricators. Well. For the polycrystalline, is around 100 and 300 euros. From the thin film, between 100 and 250. From the perovskites, from 100 to 350. In the organic case, only 50 to 150 approximately. And the amorphous silicon to 100 to 200. I think yes.
But Tito, there is no these models are not fabricated. You cannot give a price of the model if the model is not fabricated. This model, the organic solar cell, there is no real panels fabricated in organic solar cell or in perovskites.
These are real organic solar cells.
Yeah, this one, the perovskites.
The perovskites, I suppose that they are manufactured some like this, for example. No, but I don't know.
Another small critique. Also, it's very important in the other table. Sorry.
Okay.
To add some information about the market share. The market share depends a lot of the year you obtain this data. Where is this data? In which year? Where obtained this data?
It was taken from Google. So
yeah, okay. This is a critique for the to your supervisor, of course. So they look at that before today.
Okay, thanks.
Okay, another question. I have a curiosity about slide 20.
20.
20, yeah.
Yes.
You have a group of input parameters for 2 different materials. Okay. If you want to optimize the solar cells, maybe it's possible to use a different materials with a better properties. Do you have any idea about which is the most important parameter to improve the efficiency of the solar cell?
Well, in our case, we focus on optimize the efficiency of these specifically organic solar cells. And for the manufacturers, it's easier to modify the design parameters, for example, the active layer thickness, they could make a thinner film or a thing with more active layer, or for example, for the work functions, you can change the metal. So it's very easy, but change the mobility is very difficult for each material. So in this work, we focus only optimizing values that they can modify by manufacture processes.
In the material.
If you can change the material, you have other situations, yes.
This is what I asked you about that.
Okay. Well,
Not question about
yes. Mhm. The mobilities and the lifetimes are very important for each material. So if the mobility are very low, the carriers are not going to achieve the contacts. So, well, I think it's that are.
Okay. Also in slide 25, can you go there?
Sorry.
No, sorry. No, that's not the slide. Sorry. In the optimization, you showed a table with here we are. So you said that making the active layer thickness thicker in the case of the PM6, you increase a lot the efficiency because, well, you change some anode and cathode wall functions, but seems that the active layer is the most important. Why is that so? So you improve the current.
Yes.
Why?
Because when they manufacture this solar cell, they aren't absorbing all the photons that the active layer can be. For example, in the first case, with the experimental case, they are not absorbing all the photons possibly. So increasing that only 15 nanometers more, you can absorb all that photons. So you can improve the short circuit current and then you can improve the efficiency.
Yeah. And why in the other polymer the active layer is shrinking? Do you have any sense of that?
Yes, we thought that in this case, with these thicknesses, this cell has recombinations.
So
So-
it's of the lifetimes and mobility.
Yes.
Yeah, I think that a little bit more of physical discussion on that parameters will be interesting.
Okay, thanks.
I have a small question. You show the efficiency there, and you say that you can see a 7% increase in the efficiency. How realistic do you believe that result can be? How achievable?
Well, once we have calibrated these devices, changing all the parameters, for example, the work functions and whatever, this must represent the real behavior of the solar cell. So for answer your question, first, we need to manufacture this cell with these parameters and see if all makes sense.
But that's a bit idealistic, no? Because you are doing modeling, and when you model, you take a bit of a shortcut. You don't consider everything that is in reality, no?
Mhm.
Is it true? Or do you think you can achieve, when you fabricate those devices, the 24% efficiency?
Yes, why not? If we calibrate the devices and we are reproducing the behavior of all the devices with all of this data and all of these parameters, when we change it, we can reproduce in the same way the solar cells.
Is there any more question? No, so it's okay. Okay, so thank you very much,
Thanks.
Jose. And
Thanks for everybody.
okay.
Bye bye.